Robots are machines that move with purpose to achieve their goals and get work done. They move objects, and they move themselves. Roomba, the home robot from iRobot, moves itself to clean the floor of my laboratory. Now, Roomba is a mobile robot that moves and maneuvers using two wheels that are independently motorized. Compare that to Baxter, which you see here. Okay, and this arm is about to move. All right, so what's happening here is this program is built to operate each joint in turn. So it's the base joint here in the shoulder. That's operating first. Then we have the next joint, which is a hinge joint here, and a twist joint right here. I'm actually not worried, by the way, about getting hit by this robot because it's built to work around humans. Hinge joint at the elbow. There's going to be a twist joint here at the elbow. Next, we're going to go to the wrist, another hinge joint. And then there's the hinge joint at the wrist. And then right here we have a twist joint right there, followed up by our little manipulator here. There we go. Squeezing the hand. So what we've got here, which is really cool, is 1, 2, 3 degrees of freedom in the shoulder. We've got 1, 2 degrees of freedom at the elbow. Then we have 1, 2 more degrees of freedom here at the lower arm, the wrist area, and finally another degree of freedom here at the hand. So in robots, we take the complex motion of a single joint, like our shoulder joint, and we decompose it into its fundamental elements. For the shoulder, that three-dimensional motion takes 3 separate joints, 1, 2, and 3 here. Each of those joints is restricted to a single degree of freedom. In this case, angular motion in a plane that can be described by a single variable. For example, the angle between the skeletal elements. Rethink Robotics, the maker of Baxter, calls these joints here with a hinge a bend joint because the angle between those two elements changes. Okay, that's what the motor does that's inside. The other kind of joint right here is called a twist joint. Since the immediate elements don't change orientation relative to each other as a bend, they only do as a twist. So we create 3 different joints. 1, 2 twists, and 1 bend joint here in the shoulder. We decompose it in this way for 2 reasons. First reason, motors. Motors are built to power angular rotation with a single degree of freedom. For example, let me pull out of my pocket here. I just happen to have a DC brushed motor in my pocket. For example, this is a little electrical motor. It's a direct current motor, and it runs on battery. So I have a 9-volt battery here, and I'm going to connect it up. And what I want you to watch here is I've got a little piece of tape with a black dot on it, and all I'm going to do is connect it here, and you can see it take off here. So this is what motors do. They convert electrical current into rotation. Pretty cool, huh? So the motors that power Baxter's joints are also DC electrical motors, but a special kind called a brushless servo motor, which includes a sensor so that the motor's motions can be carefully controlled. I'll explain more about these motors in a minute. Now, the second reason to create 3 separate joints, control. When we decompose complex 3-dimensional motions into separate 2-dimensional ones, then the motions are easy to control and coordinate when we link up the motions of the multiple joints, right? So, let's take a look here at Baxter's shoulder and how it's built. Each plane of the joint is at nearly 90 degrees. So here's this first joint, and here's the second joint. Here's the third joint, which is at 90 degrees there. So you combine all 3, and you get row, row, row your boat, right? You get this amazing shoulder control. So if we want to control the position of this end effector, the hand, out here at the tip of the arm, then we can control these 3 motions here, and let me show you that. Let's say we wanted to pick something up, you can do it just here. Now compare those 3 joints with our shoulder. Our shoulder has more than 10 different muscle groups, depending on how you count them. You've probably heard about rotator cuffs, since we end up wrecking our rotator cuffs in tennis and in pitching, in baseball, and things like that. Your rotator cuff alone has 4 separate muscle groups. Every single muscle group has its own innervation, its own neural control, and that neural control is independent and has to be coordinated with other muscles. So from an engineer's point of view, the human shoulder is a mess, right? Baxter's shoulder is much more elegant. 3 degrees of freedom in rotation and full 3-dimensional motion. All right, let me turn this program back on. Okay, get Baxter turned around. All right, here we go. Get Baxter doing its thing again. So you can see the joints now in the elbow. Baxter has another bend joint here that allows for flexion and extension of that joint. It would hurt, by the way, a little bit if I got hit by Baxter, but it wouldn't knock me cold. Okay, so again, you see the twisting and the bending, that combination. Same at the wrist. We see a bend joint and a twist joint. All told, in the arm, that's 7 degrees of kinematic freedom. Let me grab this again, turn this program off. And then out here at the fingers, which we saw, we have the end effector that's known as a parallel electric manipulator with a single degree of freedom in translation, and that's linear motion. Now, I want to point out that some roboticists use the term end effector to refer to only what's at the end of a robotic arm, like a tool. But since arms and legs can also serve for locomotion, I use the term end effector to include where the rubber, or the paw, meets the road. So for us, wheels, tracks, and foot pads are end effectors also. Okay? Now, Baxter's showing off here its great range of motion. It's made possible by its configuration of joints and motors that are inside that drive them. And so what makes Baxter safe for humans to work with is that it has compliant actuators. So for example, see this? I can bend these joints here. They're compliant, they give way. The motors transmit their forces to segments of the arm through a transmission system internally that has springs. You can actually see a pair of springs right here in the shoulder joint that are external. So these springs mean that the joints give way when the arm hits me if I were to get in the way. Also, I can do what's called back driving the motors, which is this. I can push the joints backwards and get them out of my way. Finally, Baxter moves at speeds that don't create too much kinetic energy. So combine that with Baxter's relatively lightweight arms and padding, and it's a safe companion for side-by-side cooperation. What connects the end effector and the motor is the transmission. Gears and shafts that not only transfer the motion from the motor to the end effector, but further transform it by changing the motion's speed, leverage, and torque. Together, the motor, transmission, and end effector make an actuator. Now keep in mind that sometimes roboticists use the term actuator to refer to just the motor, but we're using actuator in a broader sense. The system that creates the movement, not just the motor. Let's look at a very simple actuator, far simpler than Roomba's wheel module. And here it is, a rubber band airplane. If you've never played with one of these, you should. They're great fun. No, of course, a rubber band airplane is not a robot because it doesn't have sensors or a control system, but is a self-propelled vehicle with a body and an actuator. Let's look at the actuator. We'll start with the energy supply, the rubber band. This is so familiar, you might not even think about what we're doing when we wind up this airplane here, and you can see what's happening with that rubber band, right? We're stretching the material. Because we're talking about a solid here, we're distorting the rubber band's natural preferred shape. And by definition, a solid wants to spring back into shape once you release it. So there we go, it springs back to shape. That spring energy is stored in the tiny chemical bonds that hold the rubber band together as a solid object. The rubber band's spring energy is a kind of potential energy because it has the potential to get work, in our case, power of spinning the propeller, to get that work and turn it into kinetic energy of spinning. So let's take a look at this a little more closely. The propeller is what we've been calling the end effector. And let's work backward from there. That's connected to this tiny little shaft right here, this tiny little metal shaft that then hooks onto the rubber band. This shaft is part of the transmission system connecting that end effector to the motor, and that must mean the rubber band is the motor. Now hold on. I told you the rubber band was the energy supply. Can it also be the motor? Well, it's both. Isn't that cool? It's a dessert topping and a floor wax. So the rubber band here acts as a motor once we have wound it up. And using a rubber band as a springy motor brings up something really important in the history of humans making actuators. Before electric motors, like what's inside Roomba's motor module or Baxter's arms, motors were animals. Think of horsepower. Water wheels, windmills, or, like in clocks, springs. Thinking about springs as motors, I can't help but think about some of the coolest mechanical machines that have ever been made, automata. An automaton is a machine with a hidden mechanism that operates automatically. Centuries ago, even a clock might have been called an automaton. But by the 18th and 19th centuries, an automaton came to mean any mechanical figure that simulates the movements of living things, especially humans. But while their movements may be lifelike, these machines aren't autonomous in a robotic sense. They don't use sensors to react to changes in the world. And they don't use controllers to change their behavior in response to the sensors. They're automatic in the sense that you turn them on, they move, and they run through their routine. In the same way that we can turn this airplane on and let it go, we can turn an automaton on and let it go. It runs through its routine and then stops, but it never changes that routine. Another thing to notice is that whereas the airplane propelled itself, an automaton sits in place and propels, moves, bits and pieces, the clockwork. So the airplane is closer to being a mobile robot, and the automaton is closer to being a robotic manipulator. Let's look at an example of an automaton that was first built about 200 years ago by the founder of the Toshiba company, Hisashige Tanaka. This automaton plucks arrows from its quiver and shoots them. Very cool. The Japanese call these karakuri ningyo, roughly translated as mechanical dolls. The actuator for Tanaka's ningyo is a wind-up spring. The energy in that spring is transferred to a slow rotary motion that spins cams that tap levers and winds up strings to pull arm and move head. This really is delicate, exquisite clockwork motion. But there's something missing from an automaton, and that's sensors. Once you set the ningyo in motion, it does its thing until the pre-programmed action is complete or the spring runs out of energy. But there's no feedback from the world. Because automata aren't autonomous in the sense we mean with robots, they can't do any of the things that autonomous robots do to give them intelligent behavior. Just because a toy or an automaton works by springs does not mean that you can't add a sensor, and let me give you an example. One of the neatest ones I know, something called a Neverfall toy. Right here. I'm going to wind this up and try to send it shooting over the edge of this table right here, and watch what happens. Oh no, calamity coming! And it didn't go over the end of the table. Let's do it again. Now watch, see if you can tell what's happening. So there it goes, off the end of the table. No. Somehow the toy is sensing the edge of the bench. How? Well, let's take the top off here, flip it over, and see if we can tell how it works. You can see there's 1, 2, and 3 wheels. A third wheel is oriented perpendicular at right angles to the others. Now, all 3 are getting power. So what is going on here? There's a set of passive wheels up front. And this is the trick, the secret of the Neverfall toy. And you can really see it here if we let it go forward. Those front wheels have to pop off here, and that pulls down that perpendicular front wheel, which then turns it to keep it from going onto the ground. So the moment that that vehicle tips to fall off, that third wheel engages the ground and spins the vehicle out of harm's way. Very cool. So we have in purely mechanical vehicles what are the beginnings of intelligent behavior, where the vehicle can respond to changes in its world. The springs in toys, automata, and mechanical clocks are very useful motors, but they have to be wound up regularly. Remember what we're doing in terms of physics. When we wind up or load a spring, we're adding potential energy to that machine by using the muscular energy of our human bodies. Energy transfer is all around us all the time, and the trick for robots is to put the energy in a form that creates movement. When it comes to creating movement in robots, I'm going to go out on a limb here and say that the most important kind of motor is the electrical motor. All motors work on a similar principle. At least electric ones do. They use electricity to spin magnets. So I've got electricity here, and I've got a motor. Let's get into the nitty-gritty. We really need to understand electricity. When we connect up the poles of a battery to the wires of the motor, the DC motor and the battery create a physical connection called an electrical circuit. The name circuit is used, by the way, because of the idea of tiny electrical particles traveling in a circuit from one end of the battery through the motor and back to the other end. The whole amazing trick of electricity is that the particles are charged in two different ways, positive or negative. All that matters for us at this point is that opposites attract. You put a bunch of negative charges on one side of the circuit, let them run into a positive attractor on the other side of the circuit. This attraction of opposites is the force that drives the flow of particles, a flow that we call the electrical current. Now we can understand the DC in a DC motor, that name. It stands for direct current. And the idea is the electrical charges flow directly from one pole of the battery here through the motor, if I were to plug this in, to the other side. Let me just do this real quickly so you can see that go. Right? In contrast, we can have an AC motor where the AC stands for alternating current. AC electricity is what comes out of your wall socket, and I like to think of the charges as vibrating, alternating back and forth, rather than traveling like water one directionally in a pipe. Here's a fun historical fact. For delivery to homes and factories, DC electricity was championed by none other than Thomas Edison. Many aspects of AC electricity were developed and patented by Nikola Tesla. What is called the War of the Currents played out in the last decade of the 19th century. Because AC is easier to transmit over long distances, it's more efficient, it won the war. However, DC is safer to work with and easier to control. So DC won the battle of the currents in terms of what we use inside appliances like computers and machines. What we need to know about batteries at the moment is that they contain two different chemicals inside. Dry batteries do like this. The battery is designed to keep those chemicals physically separate. So roughly speaking, you can think of one chemical living at the negative end or negative side of the battery, and the other living at the positive side. So I've got a positive and a negative pole here. One of those chemicals provides the charged particles, and the other chemical collects them. And they exchange those particles through the electrical circuit that we create when we put a motor in there. One more thing. You've probably heard about the voltage of a battery, since we buy 9-volt batteries, for example, and what does voltage signify? Voltage is a way to measure the strength of the attraction between the different chemicals in the battery. The higher the voltage, the greater the attraction. The greater the attraction, the faster the flow of particles through the circuit. Batteries are a common source of energy for actuators and robots, so it's really important we understand how they work. When a fully charged battery is not part of an active electrical circuit, we say that it has potential energy. That is, the separation of the charges gives the battery the potential to make the circuit work. And as soon as we turn that circuit on by throwing the switch, which I can do with this system right here too, it's just another battery. You see the gears. By throwing the switch, then we turn the potential energy into actual energy as the charged particles get moving. In other words, when we start to use that potential energy, it isn't potential anymore, it's the energy of motion in those charged particles. That electrical current, that movement of charge, causes the motor to move. This is a particular type of electrical motor, a DC brushed motor right here, that I showed you earlier. I'm going to take this one apart for you. How in the world can electricity spin a motor? Well, it has to do with the fact that inside there's actually some magnets. Isn't that cool? When we think about electricity, we're talking about the conversion of chemical energy from the battery into electrical energy of the circuit of the mechanical energy of the motor. Okay, so somehow right in here, magnets are involved here. And what's wonderful about this, if we turn a robot on like Sparky here, that's all that Sparky's doing, is taking that potential energy of the battery and turning it into motion here as soon as it warms up to power the stepper motors that are in the wheels of Sparky right here. Okay, so I just think this is great, and it's part of why electricity has been seen as magic. We can't see it happen, but we know it does happen. So I've got this other DC motor that I've started to take apart here. And electrical motors have two main parts that we need to talk about. The part that spins out of this drive shaft here that moved this flag that I have on here is called the rotor, and the part that stays still is called the stator. So let me take this apart here for just a second and show you the inside. So It's kind of hard because it's a magnet pulling it. So here's the rotor, and the inside of this is the stator. Take a look at all these wires here. Can you see that? All that copper wiring. Those wires are wound around the arms in the rotor. And now look at the stator. In this particular motor, the stator is two magnets on the wall of the housing. So you can see right away that we have a magnet and we have electricity in the motor. And how do they interact? How do they work together? Here's the trick, and it was put to use nearly 200 years ago by Michael Faraday. If you run electrical current through a wire, the flow of that current creates a magnetic field around that wire. Now what if you take the electrical wire and you wrap it circularly and then run a current through the wire? What happens? The magnetic field that is created by the flow of the current in the wire becomes strong and directed. And if you reverse the direction in which the current is flowing, then the magnetic field changes direction. Now back to the motor. When we see wires coiled like this, we know that a magnetic field is being generated. Now you know from playing with magnets, and I've got a couple here, that they can either attract or repel each other. So here they are attracting each other. And if I flip them over, so magnets have poles, I actually can't put them together. You can see it flips off here. So depending on how we have the magnetic fields oriented, we can get attraction or repulsion. And there's a connection, by the way, between electricity and magnetism. Both fields are of charged particles. So an electric motor works by creating magnetic fields that spin the rotor. Okay? And the stator creates a magnetic field, and the rotor does too. And if you are clever, like Anios Jedlik was in 1827, you can reverse one of the magnetic fields back and forth so that you can pull and then push the rotor around, right? Just like we were doing with these two magnets here, but we're using electricity here. Now, here's something to blow your mind. An electric motor, as part of an actuator, converts the movement of molecules into the movement of a robot. Molecules move, robot moves. Whoa, man. Isn't that cool? For roboticists, one of the great innovations in electrical motors has been the servo motor. Let's look carefully at this motor. Unlike a DC motor, which has two wires, the servo has three. Now, the brown and red, or it should be black and red, but that's okay, brown and red wires here are for the electrical circuit. And in fact, they go to a small DC motor inside. And I just want to take this apart for you and show you that DC motor. Here's our DC motor right in here. So the third wire, it's actually the orange wire coming from the outside, is bringing in a control signal. That's what's happening actually. The signal, which is called a pulse width modulated signal, or PWM signal, is sent to the servo from a computer. The width of the pulse, what is really its duration in time of a square wave, tells the servo where to position its rotor on a circular dial. And that signal is sent every 20 milliseconds, or 50 times each second. A kind of hyper-annoying attention to positional detail that gives servos their precision. So let's take a look at a servo motor in action. So here's a servo that I haven't destroyed by taking it apart. And notice I've marked one of the arms here in what's called a servo horn so you can keep track of it. Now I've hooked this servo up to a microcontroller that's called an Arduino Uno. And so the whole point of this microcontroller is to send that PWM signal. So I'm going to get this going while we talk here. I'm just putting it into a USB power supply. There we go. So here's our servo moving back and forth. So in order for the servo to move smoothly and slowly, the computer program on the Arduino is creating a new signal every 15 milliseconds that adds 1 degree to the previous position. So that's causing this sweep back and forth. Since the motor is sweeping through 180 degrees, that's 180 different positions being commanded in each direction. Now, we still have to answer one question, and it's really important. How does the motor know when it has gotten to the right position? You can yell at your brother all day to stop at the donut shop, but if he can't see the donut shop, then how does he know where to stop, right? So the servo motor needs something special, and it's called a sensor. Just like being an autonomous robot tracking down donuts by their smell, a servo motor needs feedback from the world. Okay, so see what we're doing here? We're adding sensors into motors. So you get that feedback from a sensor, you can tell where you are in a rotational sense. In the case of a servo motor, the sensor, which I'll point out here on this other servo, that sensor, I have to lift this up underneath here, is a device called a potentiometer. Now, a potentiometer is a variable resistor. You may encounter a potentiometer if you have ever encountered an old school appliance with a volume knob. Let me show you how this works, by the way. I'm going to unplug our Arduino and servo to keep that from going here. This is a potentiometer. So I'll hook this potentiometer up to a device called a multimeter, which allows us to read the resistance that this potentiometer creates. So, whoops. So a multimeter is a device that allows you to measure voltage, resistance, or current. And I have it set on resistance reading. And there's going to be this red dial here that moves back and forth depending on the resistance that I dial in with the potentiometer. So I'm just hooking this up with alligator clips into this machine. You can see the dial start to move here. So we're going to turn the knob and look what happens here. So I'm just going to touch it a little bit, look at that red needle, and you can see it drops. I turn it back and it goes up. So this is a variable resistor. Now, a small version of this potentiometer is built into our servo motor. The potentiometer rotates with the rotor of the motor. And let me show you the gears that are up front when I take off the top of that servo motor. And right there, I'm pointing at the potentiometer. That is geared to the motor, so as the motor moves, the potentiometer moves, and that provides feedback, letting the motor know where it is rotationally. You can think of that feedback as the answer to this question. Am I at the correct rotational position? If yes, then hold this position as long as the PWM signal tells me to. If no, then try as hard as my motor will allow me to move into that position. Servos are very eager to please. So you can see right away why servo motors are so useful in robotics. Precise control of motion. Now, here's a really awesome example of using servos for both position and propulsion. This lovely thing here, a robot called Hexy from Arcbotics. Hexy has 6 legs, hence the name Hex from Hexy, and each leg has 3 hinged joints. It's got a joint here, a joint here, and a joint here. So what we would call 3 kinematic degrees of freedom times 6, so 18 degrees of freedom. Now, I have to use my computer to get Hexy going here. As you can imagine, right, I needed one Arduino, one microcontroller to run a servo, a single servo. Now I need a much more powerful computer to run Hexy with 18 servos. Okay, so I'm going to, first of all, plug Hexy into the computer through the USB port here. And we're going to create some room for Hexy on the tabletop because it's about to do a really cool set of movements for us. So I'm going to tell Hexy to stand up. Stand up, Hexy. Ta-da! I'm going to give it a little help. The reason I'm going to give it a little help here, there we go, is it turns out that it takes tons of energy to power all 18 of those servo motors. Hexy is a great example of a biomorph robot. It's inspired by biology. If it had 8 legs, I'd be tempted to call it a spider. But with 6 legs, we should think about insects and how they use their legs for locomotion. Biology is always a great source of inspiration for roboticists. A great thing about legs is that they can also be used as actuators for other jobs, digging and probing. Now, this is usually done with the front pair of legs doing this work. Legs can pick up small rocks, letting the robot look underneath. They can turn the rock over and allow sensors to take pictures. The front legs might also place the rock into a special analysis chamber on the robot's body. Just like we saw in Hexy, the legs of insects have multiple joints. Legs and arms jointed actuators are a design that we see in many kinds of mobile robots and robotic manipulators. We have two lovely arms on Baxter. Now, let me get this program going. Baxter is showing off here with its great range of motion made possible by the configuration of its arms and the motors inside that drive them. Now, what makes Baxter safe for humans to work with is that it has compliant actuators, what Rethink Robotics calls series elastic actuators. The motors transmit their force through a transmission system that has springs. So if I grab the arm here, you can see the springiness that's in here. These springs mean that the joints give way when the arm hits me or runs into something. Also, I can backdrive the motors, push them backwards, get them out of my way. You can actually hear the actuators in there. Third and less obvious, but perhaps even more important, the spring inside makes it possible for Baxter to measure the forces that the actuators are exerting. And that means you can actually measure and have dynamic control over forces, torque, and much more. So finally, Baxter moves at speeds that don't create too much kinetic energy. So you combine that with Baxter's relatively lightweight arms, and it's a safe companion for side-to-side cooperation. Actuators of all kinds define how a robot moves, how it moves the world, and how it can, by its movements, change the world. Movement defines what a robot is. But actuators, the motors and transmissions underlying robot movement, can do other things to change the world besides move. In fact, if you really want to twist your noodle, you can think of an entire robot as one giant actuator. Servo motors, like this one, with their embedded and tightly linked internal sensors, steer us towards an understanding that actuators need sensors. For an autonomous robot, all its motors and all of the actuators that they move are responding at some level to information provided by sensors. So we turn next time to sensors. Lots of machines move, but autonomous robots need both movement and sensors to work.